Good afternoon, everyone, and welcome to the Informs Health Application Society online seminar series. We are glad to make a great start to this year so far with a line of great speakers. And today we are happy to have David with us. David is an associate professor of mathematics at North Carolina State University. His research focuses on convex and polynomial optimization with applications in medicine and healthcare. He has co-authored over 35 peer-reviewed publications in high-impact journals, and his algorithms developed at Massachusetts General Hospital for the solution of large-scale optimization problems in radiotherapy have been incorporated in clinical treatment planning software used worldwide. He is the recipient of the prestigious 2021 Sanjay and Panna Mehrotra Research Excellence Award for his sustained work on optimization methods and models for radiation therapy for cancer. He also received the NSF CAREER Award for his methodological research on efficient optimization over non-symmetric convex cones and polynomial optimization problems. So David, thank you for joining us, and the floor is yours.
Thank you, Said, for the kind introduction. And I also wanted to thank the organizers, Said, Joshi, and Sanjay, for inviting me for this online seminar series. I think it's one of the few great things that came out of the pandemic is that this seminar series started, and it's really an honor to be part of this rather illustrious lineup. So yes, and thank you all for coming. So today I'll talk about some of my ongoing and recent work in optimization radiotherapy, and about how optimization methodology can help inform medical decision making, specifically in the context of radiotherapy. And so today in this talk, first I'll give a very brief introduction to radiotherapy and how we use OR techniques and optimization in it for those of you who have not seen this before. And then I'll talk about my work using sort of two vignettes, one about treatment fractionation, which I'll introduce later what that problem exactly means, and also a more recent problem, which is I think a little bit more OR healthcare flavored, which is treatment selection and patient selection for proton therapy. And I should say that this is all based on joint work with clinical collaborators from Zurich and from Oncore, and also some of it has been done with the students and postdocs here at NC State. So as I'm sure you all know, cancer is one of the main sources of mortality everywhere in the world. In particular, even in the US, about 600,000 people die from this disease every single year, even with access to advanced forms of therapy. And there are generally 5 main types of cancer therapy. There is surgery, which is the primary form. There's radiation therapy, which is what I'll talk about today, and chemotherapy, targeted therapy, immunotherapy. So radiotherapy is the one I'll talk about today, and it's already a major form of treatment. It's given to more than half of the patients in the US. Either as the main form of treatment or as a part of a treatment that uses maybe several of these modalities. So what happens during radiotherapy is that the patient is treated with several daily doses of radiation. So this is not delivered all at once, but rather over several consecutive work days when the patient is irradiated. And most commonly we use photons, so X-rays, to irradiate the patient. But there are some other options too. These are far less common, much more expensive, but are frequently superior, such as proton therapy. I'll talk a little bit about these later on, because one of the projects, actually both of the projects to some degree, are related to this question of should we use photons or protons, or how can we use them, and what the differences are for different patients. But so the basic principle is that the radiation passes through the patient and will kill the tumor cells by damaging DNA. Unfortunately, we cannot just aim at a specific depth and at specific cells. So if we are killing tumor cells by damaging their DNA through the radiation, then the same thing happens to the healthy cells as well. So the goal is to sufficiently irradiate the tumor, but at the same time, we also want to spare the healthy tissue and especially critical organs from unwanted radiation as much as possible. And we can do this through multiple ways. One is sort of purely geometric, and it's this idea of using multiple beams. So if we use not just a single radiation beam, but we irradiate the patient from several different directions using beams that individually deliver not too much radiation, then the unwanted radiation everywhere can stay relatively low. But where these beams intersect, that's where we'll deliver much higher doses And ideally, that's exactly where the target should be. Another way to spare healthy tissue is using this idea called fractionation, which I already mentioned on the top of the slide. This is, again, this healthy tissue sparing is what motivates this idea of not delivering all the dose at once, but instead break it up into several daily doses instead of one. And I'll talk more about this fractionation shortly. So here's a simplified, kind of quick overview of the treatment planning process and how optimization OR plays a part in just about every step. So the patient first has to be diagnosed with cancer, and then they are imaged using at least a CT scan. This is what you can see here on the right. So this is like a three-dimensional X-ray scan. Here you can just see one cross-section. Sometimes other imaging modalities are also used, MRI, etc. And then the tumor and the critical organs are contoured on this three-dimensional image. So here you can already see a target volume being contoured, and then also some organs at risk around it. This is done partly manually, partly in an automated fashion. And then the physician has to provide a so-called dose prescription, which is how much dose we want to see in the target volumes, how much dose are we willing to tolerate in the different critical organs, etc. And this also includes this treatment fractionation that I mentioned. So, for example, a dose prescription in a target could be something like, let's deliver 30 times 2 grays of dose. That means gray is the physical unit for absorbed dose. So we want to deliver 2 grays of radiation at least to the target volume in each of the next 30 days. That would be 30 times 2 grays of prescription. And then all of this becomes input to step 4, which is where the treatment planner uses some treatment planning software, which is essentially an optimization algorithm with a nice interface to optimize all the irradiation parameters to achieve this optimal target dose distribution, which is what you can see here. So, for example, in this patient, you can see that they are being irradiated with 7 different beams, and they all deliver these relatively low amounts of radiation individually. But then where these beams intersect, that's pretty much precisely where the target volume is, and that's where you see the high dose in red. This last step, this optimization step, is what we mostly talk about when we talk about radiotherapy optimization. And I wanted to highlight it, although I won't talk much about it in this talk, but I really want to mention this because I think for those of you who may be not experts in this area, but if you've seen maybe just a single talk ever given on radiotherapy optimization, or you saw one paper, it's almost certainly related to this. This is what we usually refer to as radiotherapy optimization, is the optimization of the treatment plan for a specific patient. And these are very interesting optimization problems, very large scale optimization problems. So these radiation parameters that we have to optimize here, these include like these intensity profiles for each of the beams and the directions. Altogether tend to be tens of thousands of variables. So really large scale and challenging, interesting optimization problems that are of course interesting to everyone who works in optimization methodology. And I wanted to, again, just very briefly talk about this, just because this is what we usually mean when we talk about treatment plan optimization. It's by far the most well-researched step. And for those of you who may have never seen this, perhaps some grad students in the audience, if you want to look up more about this, the keywords to search for is IMRT, intensity modulated radiotherapy. This was really the first very successful application of optimization in radiotherapy. This goes back to the late 1980s, early 1990s. And as I said, this is a large-scale optimization problem, tens of thousands of variables, but with some reasonable approximations, this can be made to be a convex optimization problem. And this was sort of the first really big revolution in radiotherapy, so to speak, where we're using optimization methodology, using the same machinery and the same infrastructure that was used before in the clinic, the treatments can be improved substantially. But in spite of this being a 30-year-old area, there's still a lot of ongoing research that's going on in this field, in part because new modalities are being discovered and developed. As I mentioned, for example, instead of using photons, we can use protons. And even though some aspects of the problem remain the same, for example, the same optimization algorithms could in principle be used, but what happens with these different modalities, for example, or when some new insight from either physics or biology comes into play, is we have to revisit some of our assumptions. For instance, all of these modalities they inherently have certain delivery uncertainties that need to be handled one way or another. For example, we might want to use stochastic or robust optimization, but these uncertainties are completely different. The sources of uncertainties and the way they manifest are completely different, say, in photon therapy and in proton therapy. So even though formally some aspects of the optimization problem seem the same, if we, for example, carry over all our assumptions from one modality to the other, but more often than not, we really have to revisit those assumptions and think about the underlying application to see whether the models actually make sense and whether we can solve the new problems from the modeling side, or whether we need to develop some new methodology. So very interesting research, both in modeling and in optimization algorithms, are still going on in this area of treatment planning optimization. But what I actually want to talk about today more is the step 3, which we almost never talk about in OR context, because it seems to be entirely the purview of the physicians, right? The physician provides a dose prescription and the treatment fractionation following some established protocols and patient-specific circumstances. So these are questions like, how do we select the right treatment modality for a particular patient, or which patient gets what type of treatment? How should we fractionate the treatment? What sort of dose prescription we should give the patient? So even though this is, of course, very much a physician's responsibility, and I don't suggest that this could in the future be replaced by some algorithm, we have found in recent years that some optimization methodologies and models can really yield some insight and inform some of this medical decision making at this step already, either to provide better input for that step 4, or perhaps even by being able to join these 2 steps together. So this is what I'd like to talk about today by talking about these 2 projects that I mentioned earlier. So let me start with the first one, which is related to the optimization of treatment fractionation. And first, let me then talk precisely about what is this fractionation that I have been talking about. So as I said, radiation in general is not delivered all at once, but instead the patients are irradiated in many treatment sessions on consecutive weekdays. I keep saying, it's many treatment sessions. I never said how many. It's because it can be as few as just 2, 3, or 5, but it can be as many as 30 or 40. So this can be really substantial, large treatments that go on for well over a month. And as I mentioned, the rationale is always that the healthy tissues tolerate the fractionated treatments better, simply because the healthy cells are able to, or may be able to, recover between treatment sessions. Of course, the tumor cells also, in principle, could recover between treatment sessions, but because they get higher doses, they tend to recover considerably less. And the standard of care is that all the treatment sessions are the same. So there is no need or point to change up the treatment from session to session. We are simply taking that single dose distribution that was optimized, and then we break it up into equal parts. Okay, and this is what I'll refer to as uniform fractionation. And here there's not much of a decision making to do, because the only thing to figure out is the number of fractions. Mathematically, that's not very interesting or from an optimization perspective, and there are established ways to do this. But the question that we were studying, and this starts with the research of my collaborator, Jan Unkelbach, who a number of years ago asked this question of, could different fractions yield an improvement? So could we deliver a significantly better treatment for a patient if we changed up the dose distribution from fraction to fraction? And to study this, we first of all need a mathematical model for this fractionation effect, right? We have to quantify, we understand that identical physical doses, when they are fractionated have different effects, but precisely how different these are. So for example, if I delivered 1 gray of dose today and 1 gray of dose tomorrow, that will have some effect. We know that's not the same as just delivering 2 grays of dose today. 2 grays of dose today is more, it will have more effect, right? But what's the right number to put here, right? How much dose today is equal to 1 gray today plus 1 gray tomorrow. So one simple model that fits remarkably well, and it's well established and has been used for a long time, is the so-called BED model by Fowler from 1989. BED stands for biologically effective dose. And what this model states is that the magic number to come up with, to put here, is based on the simple quadratic formula. So this biological effect B is the total physical dose. So here we are summing over all the fractions, and this is the number of fractions. D sub I is the amount of physical dose we deliver in fraction I, like in this case, n is equal to 2. So D sub I is 1, D sub 2 is also 1. So this is the total physical dose. If the formula ended here, it would mean that there is no fractionation effect. It doesn't matter how I break up the total dose. But we know that's not the case. To come up with this biological effect where two differently fractionated dose distribution can have the same effect if and only if their b values are the same, what we need to do is modify upwards this physical dose by this quadratic term. Because alpha and beta are some tissue-specific parameters. The interpretation doesn't matter. It also turns out the individual values don't matter, only their ratio. So this is really a single parameter model, which is very nice because that means that we can have fairly high confidence that we're able to determine this. And when I say tissue-specific parameter, what I mean is that, for example, this will be different for different types of tumors, but it could be different for a healthy liver versus a liver tumor. But it's something that is not really patient-specific as much as just tissue-specific. So for a certain type of liver tumor, we could believe that we have a fixed value for this. That's well established. All right, and this is always a positive number. So what we see here is, of course, interesting for optimization algorithms. That this is a convex quadratic function. Okay, so once again, what the model states is simply that if we have two different fractionated dose distributions, and they have the their corresponding b values agree, then they have roughly the same biological effect. This biological effect is not really this b value. It's not necessarily directly interpretable, right? So if you say, okay, my b value is twice as large, it doesn't really mean the effect is twice, like it's twice as much cell kill or something. It's not so directly interpretable, but it's interpretable in the sense that if you want to minimize the biological effect, you want to minimize b. Right, so larger b means more effect. For example, in the tumor, that would mean larger cell kill. And so what do we learn from this formula already? Something very simple we can see is that for a given amount of total dose, so if I keep the sum of di's constant, and I want to minimize this, then the best thing I can do is to do the uniform fractionation, right? The standard of care, which is precisely why one would do this uniform fractionation, right? If we fractionate because we want to spare healthy tissue, then we want to spare the healthy tissue as much as possible. And for a given amount of total physical dose, the lowest b value is attained when we fractionate evenly. All the d sub i's are equal. On the other extreme, if we wanted to maximize the biological effect, then of course the best thing to do is to deliver all the dose at once, right? So that this whatever d1 squared, which is the total dose squared, that term will dominate everything else. All the other doses are zero. All right, so in other words, in an ideal treatment, we would want to fractionate as much as possible and as uniformly as possible. So as many fractions as possible and as uniformly as possible for the sake of healthy tissues. But at the same time, we would want to not fractionate at all and just deliver everything all at once for the sake of maximum cell kill. And of course, ideally, we would want to do both simultaneously, but that's nonsense because all the unwanted dose in the healthy tissue is a direct consequence of the desired dose in the tumor. So if we don't fractionate at all, say the tumor dose, then the unwanted dose will automatically not be fractionated. Okay, and so specifically, if we use identical fractions, right, as standard of care, then however much that we fractionate in the healthy tissue is going to be the same. We fractionate exactly the same in the target, which is not great. But then the observation by Unkelbach from like 2015, 2016 is that if we deliver different doses in different fractions, then we can at least approximately do this, fractionate much more in the healthy tissue than in the tumor. And here's a picture that kind of shows this how. So here, inside the patient's brain, you see two contours. The inner contour is the target we want to irradiate. The outer contour just kind of outlines this volume around the target, which is basically the part of the brain that's most at risk from over irradiation. And so what you see here is a 4-fraction treatment. Each fraction irradiates a different part of the tumor. But in spite of that, the doses in the healthy tissue, in the, say, like in this rim around the target, are fairly similar. They are much more similar than they are, dissimilar inside the target. Okay, so if you pick any cell, say in the target, let's say in the middle of this red peak, in this high dose peak, cells around here see what is almost a single fraction treatment because they get almost all their doses in a single fraction. At the same time, the healthy tissue around the target sees what is an approximately 4 uniform fraction treatment. Now, unfortunately, this is a good idea in principle, and one can even put an optimization method behind this. But the only way this was actually possible in this previous picture is that he was using protons instead of photons. Without going too much into the details, we could spend a lot of time on just this slide, but let me just try to explain this as briefly as possible. The difference between protons and photons is that the way photons work is that they simply go through the whole patient. And if we irradiate the tumor, then we are also irradiating all the volume in front of it and behind it. And in fact, we deliver more dose to in front of the tumor than to the tumor itself. Whereas with photons, we can effectively aim at a specific depth in such a way that we have some relatively constant low dose delivered to the part that's before the tumor. Then we see this sort of dose peak delivered to the tumor itself, and then suddenly the dose goes down to zero. So again, this kind of pictorially, this is the photon depth dose curve you see imagine that the beam is coming in from the left. So this is the depth in the patient. Maybe the tumor is here between 19 and 26 centimeters deep. We just irradiate the patient with a single beam. We irradiate the patient a lot more, say 4 or 5 centimeters deep, than we actually irradiate the tumor. Whereas with protons, we could do something like, let's say we just want to irradiate this distal edge of the tumor. Then we'll deliver some dose to this whole entrance region. Then suddenly the dose goes up. Most of the dose actually goes to where we want it to go. Then it drops down to zero. Why is this useful? Because now you can, I think, imagine how we could do something like, for some of the fractions, irradiate maybe just the distal parts of the tumor, and in some fractions only irradiate the proximal part of the tumor. The entrance dose is about the same, and the exit dose is about the same because it's zero. So we have very similar doses outside the target, but we have much more dissimilar doses inside the target. Okay, so we can do this very naturally with protons, but there is no equivalent of this in photons. And that's a big problem because proton facilities are much more rare and much more expensive. So this was unlikely to become something like a standard of care unless we can do this with photons. And so this is what we started studying a couple of years ago with Jan and also with a student and a postdoc of mine here at NC State. How can we do something like this with photons? And again, the problem is, I showed you this picture here earlier. If we have say like a 7-beam treatment, like what you see here, if we try to do something like irradiate only half of the target in one fraction, the other half in the other fraction, we are basically just splitting all these beams into 2 halves. And so again, we have the same problem. As much as we fractionate in the target, we also fractionate outside. It's not going to work. But what could work in principle is if instead of delivering a treatment like this, imagine a version of this treatment where all the unwanted dose is not in these like 7 distinct directions, but instead it's kind of smeared out all around the patient. It's still the same amount of total dose. The patient doesn't get more dose, but it's more evenly spread out. Then in this sort of low dose bath around the target can be much more similar, no matter which part of the tumor we focus our radiation on. So again, this is just something that in principle one could try to do. The question is, can we actually put the optimization method behind it, first of all? And second, can this be really good enough that it's actually worth it? Because one problem that arises with this kind of treatments is that if all the fractions are completely different, then, for example, that means so much more planning time, so much more quality checking time. This might require new software. It will require more training for staff. It's quite a bit of a logistical issue to introduce something like that into the clinic. It's not something that we can just switch over from one day to the next. Is it really worth it? How can we evaluate whether this is worth it? So let me first talk about the optimization part. So this is very similar to the standard IMRT model that I mentioned, the classical physical dose-based optimization in radiation therapy. But we have to incorporate objectives on this biological effect that comes from the BED model. Also, very importantly, we have to optimize simultaneously all the fractions. This is maybe not obvious, but I wanted to mention this, right? Because we don't know, we don't have this initial partition that I showed you in the initial figure. We don't really know what parts of the tumor we would want to irradiate, say, in different fractions. That partition itself comes out of the optimization method. So the only way we can do this is by simultaneously optimizing all the fractions at the same time. So this is an n times bigger problem, where n can be, as I mentioned, could be as little as 3 or 5, or it could be 30 or 40. And because we are switching to the biological effect, the BED, instead of the physical dose, constraints that are nice and convex and mostly even linear in the standard IMRT model become non-convex quadratics. So even the simplest formulation of the problem ends up being a very large-scale non-convex QCQP. And I won't bother you with the details again, in part because of the lack of time, but I wanted to just maybe very quickly walk you through, just to give you an idea of how a problem like this could look like. So the main optimization variables are these x sub t's. These are basically those irradiation parameters that we want to determine. The subscript t denotes the fractions. So we are optimizing the n fractions simultaneously. Each of these x sub t vectors define the radiation parameters for one fraction. So these are, again, the dimension is in the maybe low tens of thousands. Then from there, we can compute the physical dose d sub t through some known matrix d. So again, these d sub t's are basically, you can think of it as like auxiliary variables. These won't be in the final optimization problem, but it's just here for didactical reasons. Again, the dimension of this is in the millions or tens of millions. And then from the physical doses, we can compute those BED values, right? This is the same formula as what we had there, but for each voxel, each little volume element where we compute the dose inside the patient. And once we have these BED values from the BED model, now we can sort of cut to the meat of the problem. We have a variety of objectives, and there are many ways to set this up, but the way we set this up for this particular problem here is that we use a reference plan, which is basically that optimal uniformly fractionated plan, right? Like the standard of care plan, which itself comes from a multi-objective optimization problem. I didn't mention this before, but I think it's fairly intuitive. All of these problems are really inherently multi-objective problems because we have several organs of risk to spare. Usually the more you spare one, the less you can spare another. So you want to find a good trade-off between irradiating the different targets and sparing the different organs. So you have various clinical objectives. What we did here in this problem is we set our optimization model up in such a way that the plan we are trying to compute now, where all the fractions can be different, we call this the spatio-temporally fractionated problem. In this new plan, we do at least as well as the reference plan with respect to every single objective. Okay, so with respect to every clinical objective. And then we have a sort of a primary objective, which is the one that measures really the benefit, right? That has to be a scalar ultimately. Even if it's a multi-objective problem, usually there is some kind of a primary objective, which is what we use to measure the benefit. Frequently, this is the dose to a dose-limiting organ. For example, if you're treating a liver tumor, most likely the biggest issue is going to be that the healthy liver gets too much dose. So the biggest benefit you can hope to achieve is a reduction of the healthy liver dose. Then we will put that here as the primary objective. Okay, so this will be our problem. Of course, we can still choose these objectives in all sorts of ways, and there are many ways to do it. One of the simplest ways to do it is to just choose convex objectives. Here, for example, we use some a convex piecewise quadratic function. This will be good for, say, a target volume where we have a prescribed BED value that we want to see in the target, and then we are penalizing quadratically this like the underdose, essentially. Oh, and I saw that there was a raised hand, I think, but it just kind of disappeared from my screen. So if anyone has questions, I'm happy to stop. Or if not, then I'll go on. I can't hear anyone. Unfortunately, I can't see much else other than my slides. So
yeah, David, if you want, we can have the questions at the end of the talk.
Okay, I'm fine either way. Yeah,
okay.
Maybe.
Then if I see anything on the chat, I'll let you know.
Okay, yeah, just let me know. That's fine. I'm really fine either way. So yeah, so that was our problem. Again, it's if we have these piecewise quadratic objectives here, then we can turn this into a large-scale QCQP. And this is what we try to solve. So again, the problem is it's non-convex. In principle, many local optima may exist. And in fact, many of them do exist. We did find this, that we can easily get stuck in different local optima. This is not just a theoretical problem. And of course, it's always hard to tell whether a good local optimum is the best we can do or not. And this is particularly an issue because remember, we were doing this study not because these patients are in the clinic and we are trying to compute the best possible treatment for them or a good enough treatment for them. We are also trying to figure out what's the maximum benefit that we can achieve. And in particular, if our whatever local optimal solutions are not good, then we are not really sure whether the problem is that this technique is just maybe not really good enough for a certain class of patients, or whether there is a lot of benefit to be had, we are just not able to find it due to poor local optimization. So it's important that we are able to compute rigorous lower bounds on the minimum, not just to use that, say, in a branch and bound framework or something, but even just to be able to say what are some cases, what are some classes of patients, for example, where this benefit must remain small, and what are some classes of patients where this benefit can be large. So we try to compute some rigorous lower bounds on the global minimum of these non-convex QCQPs, and we use semi-definite programming to do that. This is a fairly standard technique. Again, if you've never seen this before, then this is probably not the right talk to learn about this, but just very, very briefly, the standard SDP relaxation works in such a way that one can show that any QCQP, convex or not, can be written as a semi-definite program with some additional rank constraints. So all the difficulty and all the non-convexity is pushed into the rank constraints. Then we can drop those rank constraints, and then we have a convex relaxation. This is not too dissimilar from how we go from, say, a mixed integer linear program to a linear programming relaxation by dropping all the non-convex stuff. And just like in integer programming, we can further improve the bounds from the convex relaxation by adding valid inequalities. So that's what we did. Again, the details of this don't matter at all. I only put this here to impress upon you that this is a very large scale semi-definite program that comes from a relaxation of an already large scale QCQP. We were able to solve this though, however, approximately. And I wanted to show you a couple of results. Again, not so much to show you something like the quality of the results, but I wanted to give you an illustration of how we can visualize these results, how can we quantify things, how can this be actually used to talk to physicians about this, basically. So here's an example of a patient where we optimized a 5-fraction treatment. So this is a liver tumor. This large red contour here is the liver. It has 2 lesions in it. And you can see the 5 dose distributions that were optimized using that QCQP that I mentioned. And I think it's already, for example, remarkable, as I mentioned, it's really not going to be easy or obvious to figure out how to partition the target volumes. For example, if we try to just deliver those to maybe to the larger lesion in 3 fractions and to the smaller lesion in 2 fractions, then we have the problem I mentioned before, that you will see the same kind of fractionation in the healthy tissue, so there won't be any benefit. This can only yield a benefit if you get these weird looking dose distributions, which are very dissimilar from each other, but might irradiate different parts over multiple parts of multiple lesions at the same time. But this way, it is possible to make all the healthy tissue doses look very similar, so that the healthy tissue sees an effectively uniformly fractionated treatment, even though the treatment is completely non-uniform. Now, still, if you look at just these top 5 pictures, it's very hard to tell. I think it's impossible to tell whether this is useful or not, or is this beneficial or not. At least one could do maybe just some reality checks. For example, I think it's very comforting that you see that the dose gradient, how quickly the dose falls off, is much sharper near the boundary than within the tumor, which has to be that way if we want to spare healthy tissue and things like that. And you can kind of visually see already that indeed the healthy tissue doses are a lot more similar than the target doses. But there are much better ways to visualize this. So I wanted to show you this here in the bottom. So what you see here in the left is our reference plan. This is that uniformly fractionated standard of care. You could deliver this by, divide this dose distribution by 5, deliver it in 5 consecutive work days. That's the standard of care. What you see here in the middle is actually a composite plan. It's a picture that was computed from these 5 pictures on top. This looks like a physical dose distribution, and that's important because that's exactly the goal, but it's actually not a physically realizable plan. You could not deliver this. This was just computed in such a way that, imagine if this were deliverable as it is shown here, then if you delivered this 5 times in 5 equal parts, then the resulting plan would have the exact same BED everywhere as this 5-fraction plan. Okay, so the effect of delivering this one in the middle in 5 equal parts is the same as the effect, the biological effect of this 5-fraction plan. And now, because these are both in the physical dose space, they are both on the exact same scale, these are directly comparable. So when you see that over here in the healthy liver, there is sort of medium dose, is greenish, yellowish dose, whereas here it's all blue, it's much colder here. That's an explicitly interpretable difference. You can literally take the difference and see that indeed the 2 doses have basically the same effect, and it's equivalent to delivering the same doses in 5 fractions in both lesions, but there is substantial liver sparing, right? And even the scale, the numbers are interpretable, right? So this 11.9 grays, the whole treatment here, the prescription would be 5 times 10 grays, so 10 grays of dose to the tumor in each of 5 fractions. So 11.9 grays of sparing in the liver basically means we spare the liver as much as if instead of delivering 5 fractions, we only deliver 4, right? It's not a question of whether this is a substantial benefit. It's clearly a substantial benefit. If you could reduce, right, you deliver the same effect to the targets, as the reference 5 fraction treatment, but the effect on the liver is as small as if you only delivered 4 of the 5 fractions, then that's a very interpretable difference, is what I'm trying to say. Okay, and so we can use these pictures to kind of get a sense of how well this works, and then of course we can do this for many patients and you quantify these differences. Just wanted to mention, of course, we didn't just do this for one patient, but for a set of patients with different geometries, studying what happens with large lesions versus small lesions or multiple lesions, etc. And we saw that, consistently there is a large reduction in the average liver BED. So here the yellow bars represent the BED of the reference plan, and then the blue bars represent the spatiotemporal, the new plans. And I just wanted to mention, because I thought that from the methodological perspective or theoretical perspective, this is very interesting, and I have no understanding of this, but the black bars here, these horizontal bars, represent the semi-definite programming lower bound. So we actually did find that even though there are different local optima, and it's easy to get stuck in non-optimal local solutions, the semi-definite programming lower bounds for these non-convex QCQPs were remarkably close. So both the semi-definite programming bound is sharp and many of the local optima are sharp, which, even though they are not the same. I've not seen this in general for QCQPs, but if there are QCQP experts in the audience, I would love to hear what could be causing this. But this is just a little methodological side note. So this is all I think I had indeed from this first project to say about the first project, and then there's still some time. I'd like to talk then about the second, a very different kind of problem or set of problems, which has to do with patient selection for proton versus photon plans. So as I mentioned before, both of these modalities have their advantages, but protons are frequently seen as superior, but they're really much less available and much more expensive than photons. Here's a little chart comparing the two. Let me just draw attention to the last line. Photon therapy is what you can get basically everywhere where there is radiotherapy administered. Proton therapy is administered at about 100 locations worldwide. So this is really much more expensive and much less available. So even though, sure, many patients would benefit from proton therapy, it's simply not possible to give them all proton treatments. So, I mean, there's also, of course, the question of which one is better, but that's, again, from a mathematical perspective or OR perspective, it's a very easy question, right? In principle, you can compute the best proton treatment for every patient and the best photon treatment. Of course, I mean, logistically, it's more work, it's more cost, etc. But in principle, it's doable. You can compare the two plans, decide which one is better. And this is actually something that has been done a lot in so-called treatment planning studies, where, again, they do this specifically to quantify the difference, for what classes of patients, what types of tumors, etc. Would it really make sense to use protons? But again, while there's a lot of value in these studies, it's not something that, it's not an OR question. It's not something where I think we can really contribute anything. But where we can contribute is that in these cases, patient selection becomes very important, right? If we find that for a lot of patients, protons are better, but they can't all get proton, then who should get the proton treatments? And this is made all the more difficult because this has to be done in an online decision-making manner, right? The decision on the treatment has to be made as soon as possible after the patient presents. The scale of this is on days, right? So a patient comes in one day, it takes a number of days to do all the imaging, the treatment planning, etc. Maybe there's consultation with the family, insurance company, whatever. After a number of days, the decision has to be made and the treatment needs to start as soon as possible. All right, and of course the clinic's goal is just to maximize the benefit over all the patients, and the easiest way to measure this is basically by minimizing the expected number of complications in a particular cohort of patients, right? Like all the patients who are eligible for proton therapy. So we studied this problem, and of course, many people have studied this problem before us as well. The basic principle is that we just have to select the patients based on some kind of benefit threshold, right? So you look at the difference between the proton and the photon. You understand the proton is better, but you have to see how much better. If it's substantially better, then you do this. Then you send the patients to proton. And some current systems already are in place. In particular, in the Netherlands, proton therapy patients are selected in this manner using fixed delta and TCP thresholds. So let me quickly explain what this is. It's really not complicated, at least on the surface. It's not complicated. The details get complicated. But NTCP stands for normal tissue complication probability, which is exactly what it sounds like. Is the estimated probability of some common endpoints. So you can fix a particular outcome or adverse effect. For example, the patient having a dry mouth from the irradiation to the salivary glands, and then you can estimate the probability. You know, if the patient gets this much dose there, then what's the probability that, you know, a number of months down the line they will have this problem? And this can be done based on, you know, dosimetric parameters. One can estimate this probability essentially just by, you know, having observed a lot of patients. And of course, this can only be used for certain conditions where we have, you know, widely accepted models where there's plenty of data and we can really understand the relationship between the dose distribution and the complication probability. So for example, in the Netherlands, the way this is done is that depending on the particular endpoint in mind, you know, they grade those. So some of these adverse effects are very mild. They're basically, you know, they don't really affect, say, the patient's quality of life in any major way. Whereas some other ones, like a grade 2, could be something where already some medical intervention is needed to counteract the problem, right? And something like grade 5 would be that the patient could die because of that adverse effect. And so depending on how bad the adverse effect is, they want to see a large enough difference between the probability of that adverse effect, right? If it's a very mild inconvenience, then protons will not be used just to prevent those. But the difference can be as small as just a 2% in the probability of 5% for some severe side effects, where already the patient will be eligible for protons. But again, the important thing is these are fixed. All right, and this delta and TCP, again, is just the difference between the estimated proton and photon complication probabilities. And so again, the basic questions we were studying, so what should we do and can we do better than something like this when a patient with a given delta and TCP presents at the clinic? So again, to study this, we need a bunch of assumptions and model inputs. First of all, we have to fix one particular indication to study. So let's say we were studying in one of our studies, we were studying head and neck squamous cell carcinoma. It's a particular type of head and neck tumor. We need then a delta and TCP model for that particular indication. This is something that in principle is easy to do. It's not something that, say, I could do easily. You need a lot of access to a lot of data. Right? If you have a lot of past patients and you have you know, the follow-up data on whether they had that indication or not after proton or photon treatment. Actually, sorry, for the delta and TCP, we don't even need that. We need just a lot of patients for which we can see we can compute the optimal photon and proton plans, essentially. And then from there, we could see what will be the resulting delta and TCP. So with enough data, we can essentially fit the probability distribution to the delta and TCP values. So we are able to say when a random patient comes tomorrow, their delta and TCP, which is a random variable, has a known distribution. Of course, then we have to study possibly the uncertainty in the distribution, etc. But then we need the patient arrival model. That's even much simpler. We don't need anything even as detailed or high resolution as a Poisson process, because we don't need the actual arrival time of the patient. Like I said, everything is happening on a scale of a couple of days. So what matters is what day a patient comes, right? So we basically just need what's the probability that on any given day, no patients present with this particular condition, let's say the HNSCC. What's the probability that one of them present? What's the probability that two of them present, and so on? I usually have fewer than one new patient per day, so this is very easy to come up with these numbers. And then finally, we need some model for the proton facility. And what we were doing here is we basically just assume that we have a fixed number of proton slots, like a fixed number of appointments available for patients. And again, the important thing here is that And we just assume that this would be really the simplest thing to do is that, once a patient is given a slot, right, once they are assigned to proton therapy, remember that means they'll receive all of their fractions with protons. Therefore, they lock others out for that many days. And this is what makes this question, interesting and also important, right? Because these treatments can be as long as, 30, 40 fractions. So you can give a treatment slot to a patient who has a reasonably high delta NTCP, but then over the next month and a half, other patients may come with even larger delta NTCP, and they are locked out of the system because we gave the proton slot to a less benefiting patient. So like I said, the basic approach is threshold-based strategies where patients above a certain threshold are eligible, assuming that there is space. First come, first serve would be a special case of this where the threshold is 0. And then, of course, we have a basic trade-off, and this is sort of the danger that if we have a very low threshold, then we can get better utilization, but the more benefiting patients may not get a spot. So and at least it's straightforward to optimize just by simulation, because here we know all the parameters. So if you fix a threshold, it's easy to simulate this and measure the benefit. Then what we studied in addition to this is a state-dependent threshold. So we're wondering whether there would be any meaningful benefit from changing the threshold based on how many patients are currently in the clinic and how much longer do they have left from the treatment. And this could be modeled and optimized using a Markov decision process. So again, just very briefly, because I'm also sort of starting to run out of time, but just wanted to give you a few pictures and a few results. So the average benefit for a fixed threshold, like I said, it's very, very easy to simulate, but still it's worth doing it because I think there are some insights which maybe in hindsight are obvious, but I think it's worth looking at. So what's clear is, as I mentioned, so here what we plot here is what's the benefit, right? Per patient. So on average, how much is the difference in NTCP? And here on the left is the first come, first serve. And you can see it does get better if we raise that threshold. So it makes sense to raise the threshold. But what I think is more important, and maybe it's not obvious, and we found this to be true for a wide range of parameters, that there is a rather sharp drop-off in the benefit. Again, it's clear that in the limit, if the threshold is very high, that means we are not treating anyone. So the benefit is 0. So it's obvious that it's always a bigger problem to have a threshold that's too large than a threshold that's too small. But just, how quickly the benefit can drop to 0 by a little bit overestimating the necessary delta NTCP threshold, I think that was not obvious. And I feel like this is one of the ways in which these state-dependent policies are actually useful, because state-dependent policies, unlike these fixed threshold policies, they are basically automatically adaptive, right? So we are less exposed to this risk of what if we overestimate the right threshold. So we studied this specifically, and I have very little time, so I'm not going to get into the details. It's really straightforward setup for the Markov decision process, what the states are, what the actions, the reward, the policy, and it's a fairly straightforward policy and value iteration to optimize this, although again, the size of the problem is what poses some challenge. But one thing we did find is that if we do this state-dependent policies, the thresholds vary quite a bit based on how many patients we have in the system. So what this picture shows is what would be the threshold if, let's say, the whole system is empty. Nobody is undergoing treatment, versus in this corner, this actually represents not when everything is taken. In this picture actually represents where one treatment slot is immediately available, but the other 2 will not be available for 30 more days. And you see that the threshold goes up quite a bit. So I think that's maybe one thing that's somewhat remarkable. But what's more interesting is, we studied this question of what happens if we misspecify the parameters. So here we have some, average benefit values per patient for different estimated arrival rates. Specifically, we've studied this. So we have a fixed, this is the true arrival rate. So this basically means on a given day, on average, 0.2 patients come. This is the true value, but imagine that we overestimated this. This is maybe not the most likely error to happen, but it's good, I think, for a simulation study, because again, what's going to happen is that if you overestimate how many people will come in the future, then you will automatically be raising the thresholds, right? That's very natural. And that's where we will see a drop in the benefit. And indeed, you can see that in the case of the constant threshold, the benefit drops quite a bit faster than in the case of the state-dependent threshold. So even though with correct values, there's actually almost no difference. You would say, okay, if you just look at these two numbers, obviously it's not worth doing this, because the benefit is almost the same for the optimal constant threshold and the much more complicated state-dependent threshold. But the state-dependent threshold, even though we didn't do any kind of robust optimization, but just inherently by the nature of state-dependent policies that will automatically lower the threshold when there are few patients in the system, it's automatically much more robust against this misspecification, even gross misspecification of the parameters. So to summarize, I think that OR and optimization continue to inform decision-making in radiotherapy, and this is true both for individual treatments, which are more like sort of medical decision-making, like what you could see in the first half of the talk, and then also in these more like resource allocation type problems that are more of the sort of healthcare decision-making in radiotherapy. And I just meant to mention, of course, there are always more unanswered questions than what we are able to answer, so we have all kinds of ongoing work. For instance, I talked a lot about both protons and photons, and also how we can deliver different fractions in different, different dose distribution and different fractions. Naturally, one could ask, why don't we just combine the two, right? We could have sort of the best of both worlds. Protons are good for some things, photons are good in other ways. Maybe we can design a combination treatment that uses both photons and protons, and it could be better than either of them individually, but at the same time, we will be using fewer proton resources than if it was a proton-only treatment. Sounds almost too good to be true. And also, it's important that, once again, there's a lot of logistical issues associated with this. Again, the optimization is the easiest part, but like I said, Proton is much more scarcely available. So even where it's available, it frequently doesn't mean that it's available in the same clinic. Just at the end of the hallway, turn right or left, and one is protons, one is photons. A combination therapy might mean that for some of the treatment sessions, the patient has to go to another hospital, or possibly to a nearby town or something like that. So it's not something where that we can logistically easily do. And there's a lot of additional constraints that we have to consider when we think about what would be a reasonable policy or a reasonable treatment strategy. And of course, the patient selection and treatment slot allocation problems this way becoming much more complicated than in the case that we studied. So that's all I had for today, and I'm happy to entertain any questions.
Thank you so much for the great talk, David. So we have time for some questions. If you have any questions, please feel free to write them on the message window or using the Q&A platform.
If I may, can I ask a question first?
Yes, go ahead.
Yeah. Thanks, David. This is really interesting talk. I'm particularly interested in the second, the proton versus photon dilemma here. I think on the very restricted healthcare resource, I think the prioritization patients is always a very interesting question to look at. So first question is more about the context. So why the whole facility is locked out because of one patient is in the treatment session? It's because
sorry, maybe I didn't speak, I think, very clearly. I don't mean that the whole facility is reserved for one patient. What I meant is that because a treatment consists of, say, 30 appointments, so when you assign a patient to protons, it's not like they are given one appointment, but you block this, 30 consecutive appointments, right, on 30 consecutive days. So
on those 30 consecutive days,
blocks in the scheduling, locks out a lot of, for a long period of time, right? That particular appointment, which is not the whole facility, but
okay. So
one treatment room in one clinic for one particular time period of the day will be unavailable for the next 30 days.
Okay, I see. Okay. Yeah, so then the second question is that you formulated this as MDP. You briefly touch upon the high dimension stuff. So I'm curious, how did you eventually solve it numerically?
Yeah, we solved it actually just about the most rudimentary ways possible, just letting it run for long enough. To be honest, we didn't do anything very
still
smart.
Solvable.
It was still solvable, but I should say, again, this was a fairly preliminary study. So the parameters were not the dimensionality was not as large as it could have been.
Okay.
So I think that there's if there are interesting, or not interesting, what's the word I'm looking for?
real world
if there are some high performance MDP algorithms that would work much better for large scale MDPs than the standard sort of elementary methods, then we would have use for those for sure.
All right, thank you.
I have a quick follow-up question on that, David. So have you considered the heterogeneity in the number of appointments necessary for each patient, the N that you choose in your MDP?
Yeah, that's an interesting question and a good one. The reason we didn't have to consider in our study is, again, because to be able to quantify this benefit for a particular indication, we are fixing, say, these head and neck patients. So there we have a standard 30 fraction regimen. So in that case, the N will be 30. We would certainly have to consider this if we, for example, considered multiple patients who come with different indications. Again, the problem then, I think, and there are all kinds of problems there. One of them is that whatever sort of overall benefit we see, it's very hard to tease apart where it exactly comes from. Mm-hmm. So again, this is not something where we solve this optimization problem and now we have a recipe for what the clinic should do. This is more like we solve this optimization problem to get some insight into the order of magnitude of the benefit that one could have.
I see.
That makes sense. Okay. So for sure, so again, the issue is then if you have, say, patients with different indications, then they have different NTCPs, and then you have to start thinking about things like, okay, how do I trade off a patient who comes with this condition and where the main side effect is that, and it's not quite as debilitating as the most common side effect of a different type of patient, right? And one needs 20 fractions, the other one needs 30 fractions, but the 30 fraction one could have a larger reduction of the probability of their not quite as debilitating side effect. Now, how do you model this? And it just becomes a mess. And at the end, you get something like, okay, the benefit is 3.8%, and nobody knows what that means. Right? Whereas if you fix one indication where there is an established delta NTCP model, and where we can understand, whether 3% is a large enough difference, or only 10% is a large enough difference, then we can get something interpretable out of it. But then one of the things that we gain with this is that, for example, the N is homogeneous, it's just 30 for all the patients. It also means that we can make that assumption that in the Proton facility, not the whole facility is available for patients with this particular head and neck cancer, which means that the number of appointments, in fact, are small, which is what, going back to Josh's question, that's why our state space is small enough that we could solve the MDP without thinking about more advanced algorithms. If you had to schedule all of the appointments for all of the patients, that MDP would not be solvable using the standard methods.
Mm-hmm. Yeah. So it's just that like the heterogeneity of N would make the optimization problem more interesting, because like if someone is asking for let's say 5 appointments, then it's like, then maybe you can be a bit more, let's say, flexible, right? Compared to like a 30 appointments blocking. But I totally understand.
For sure. I think, in principle, the optimization could be the same in the sense that the MDP model itself, which I didn't really talk about, like what's the state of the MDP model and what the actions are and all that. I think that these actually it will be straightforward, I think, to change the MDP formulation itself. Mm-hmm. I think the difficulty is in part in the solution if the MDP has a much larger state space, and also much more importantly than just the interpretation of the results. But the MDP is fairly general. We actually considered several different versions of this model, and everything can be incorporated in this MDP that we tried. We didn't really have a version of this. This includes, for example, just in the patient arrival model, right? You could have different probabilities, right? What's the probability that a patient who needs 5 fractions comes? What's the probability that the patient who needs 30 fractions comes? Mm-hmm. That's not really difficult, I think, to incorporate in these models.
So unfortunately, we took all the time for the Q&A, but there are some questions from the audience, mm-hmm. And if you'd like to answer them briefly.
I'm happy to stay a little longer to answer the question. So I see questions both in the chat and the Q&A. So
Yes, so I think the Q&A question came first. Said Mohammed Hussein asks, how does the time left between fractions affect the linear quadratic model?
That's a good question. The basic linear quadratic model is for basically daily fractions. And for small enough doses, the general principle and the understanding is that whatever recovery is possible happens within a day. So larger times don't really make a difference. If you left much more time, then the BED model would not be quite so applicable, because the more you wait, the more you have to incorporate some other temporal effects, tumor repopulation and things like that. So we want that, which is why they do this on a daily basis. One day is enough to for recovery to happen. Much shorter, like an hour or something, would not be enough. So 1 day is pretty much the thing that we do, and then the linear quadratic model applies nicely.
All right, the next question is from Mayubai. Compared to Proton, Photon may cause more toxicity and more negative impact on patients' quality of life after treatment. Is there a way to capture that aspect of difference between two modalities?
Sorry, I'm not sure if I understand, and I don't see them. Let me just see if I can. I see. I see. Photon is there a way to capture that aspect? So that's precisely what the delta NTCP captures, right? So if you have more toxicity from photons, that means that there's a higher normal tissue complication probability, right? So a larger toxicity means positive delta NTCP, and the larger delta NTCP means a bigger difference. Now, again, the quality of life differences specifically, these are incorporated essentially by the grading that I mentioned. That again, we don't just say a delta NTCP of 10% is too high and delta NTCP less than 10% is not too high. That really depends on what complication we are talking about. I hope this answers the question.
Yeah. So the next question is from Suhail Hemati. They're thanking for the interesting talk, and they learned a lot. My question is, when we have more than one normal tissue around the tumor, how would you combine NTCP values of different organs at risks to obtain the delta NTCP? Yes,
that's again a tricky question that I don't think anyone has a perfect answer for. Again, in our study, precisely for this reason, we considered a situation where there's really one or at most two primary side effects that we need to worry about. Again, if you need to combine NTCP, you don't even need necessarily multiple tissues. Even for the same tissue, you could have different side effects materializing with different probability, or indeed for different tissues, you could get different adverse effects, which can have different severity. So again, I suppose one relatively simple thing to do would be to just take some sort of a weighted sum, because again, remember, the NTCP ultimately just gives you also, you can think of it as a probability, but also you can think of it over a cohort of patients is the expected number of times you see that that side effect or that adverse event happen. So one could certainly take something like a weighted sum where the weight depends on the severity or the grade of that particular adverse event. But I don't think that there is a perfect way, or like a provably optimal way to find those weights. So there's a modeling decision to make there, not too dissimilar from like any multi-objective optimization setting where we have different objectives. One way to handle it is take a weighted sum.
Thank you, David. And there's also finally a comment from Mark Van. He says, when you need to commit to multiple appointments and making the first one, a planning optimization approach was developed by Givandelis Hawkinson and me. And continuing this comment, it was set in the context of managing a clinical trials research unit. It had a larger scope than you need. However, this planning model can be used for scheduling. This approach may be adapted to fit your problem better.
Yeah, thank you for the information. I'm going to check that out.
And if there are any other questions from the audience, I think like they would be happy to have them offline. And thank you all for attending, and thank you so much for joining us today, David.
Thanks, Said, and thanks everyone for coming.
Bye now.